Pleasure to introduce you to the second day of the PASC conference for a very special format that is also a characteristic of this conference, and that's the Interdisciplinary Dialogue. And we're very pleased this year to have an excellent speaker. We have Honore Walther, who will be discussing simulation across scales. And the dialogue would be hosted by Marina Marinkovic. I will say a few words about our interviewer and interviewee. So for Marina, who's an assistant professor in computational physics at ETH Zurich, working on high-performance computational physics, investigating the interplay of theory of strong interactions with the quantum theory of electrodynamics. Marina has had an academic career with significant mobility from the University of Berlin for her PhD to the University of Southampton for postdoc and CERN as a senior research fellow, and then for a junior professorship in LMU and Trinity College Dublin for an assistant professorship. And finally, since 2021, I'm very happy to welcome her as a colleague at ETH Zurich, where she has also recently been recognized by the Google Faculty Research Award for the exciting research that she pursues. And then for our interviewee, who will be discussing a bit on his research later during the dialogue, this is Honore Walther, professor at Technical University of Denmark, working on the field of computational fluid dynamics with a research focus across scales as the focus of our dialogue, from nano to kilometers. We will hear a bit more on this later. And he's it's interesting to say that he has also been associated until very recently, until March 2023, as a research associate at the Computational Science and Engineering Laboratory at ETH Zurich, where he worked on multiscale modeling, coupling atomistic and continuum descriptions of fluid flow. So with this, I will actually give the floor to our interviewer and interviewee to discuss today's topic.
Thank you. Thank you very much for the kind introduction, and thank you very much for the organizing committee for inviting me. It's nice to come home again. Switzerland has been a home for 25 years, so that's nice. And thank you for that's CSCS for hosting this. This is really also coming home to CSCS. So as you said, I will introduce the simulations that we're doing across scales from atoms to vortices. Here's a quick agenda, something a background and motivation, something on nanoscale fluid mechanics, so we start at the small scale. Then we move to intermediate scales where we do multiscale modeling and simulations. And then I would like to try to convince you that maybe we should treat the flow Lagrangianly, so we follow the fluid elements instead of just tracking things in and out of a mesh. And then some applications of that, and then a summary. So I will be a little fast because I have many slides. So the background is, if you like, if you go from atoms to vortices, this has been done before. There was Lord Kelvin proposed that in 1867, that maybe we can describe the atoms as vortices of different complexity. So the hydrogen atom will just be a single vortex traveling through space, described by a continuous function, and the higher order elements would then be more and more complicated vortices that would have knots on them. We know that this was not a very successful model, later replaced by Bohr. So what we propose is the opposite way, that we describe continuous or discrete fields with particles. So here's some examples of that from the left to right. And top to bottom, you see atomistic simulations of flows in a nanotube. You see solute dispersion, you see spray formation, you see ice breaking, you see astrophysics. And on the bottom right, you see that we are doing continuum fluid mechanics using particles, and those particles then describe these continuous fields. And you can ask, what is the advantage of doing that? And one thing is, when we derive the Navier-Stokes equations, and sorry for bringing equations so early in the morning, you'll see that we have this, we compute, the change of momentum of the fluid elements will change due to pressure and shear, as we know. And we normally don't like to solve this because we need to go with the flow, so we discretize it using Reynolds transport theorem, and then we discretize that on an Eulerian mesh that may or may not have a velocity depending on the application that we are studying. Of course, if this mesh would move with the flow, then this nonlinear term that is the driving force of the beauty of fluid mechanics will then vanish. At least we don't have to take it into account. So you can say, if I do this, if I have a mesh or a discretization that follows the flow, then you will write it like this. I follow the fluid elements with a local velocity that depends on the presence of all the other particles, depending on how they interact. And the properties that they carry may also change due to a right-hand side. Now you can ask, what is the advantage of that? Well, if you go with the flow, you probably adapt to it and you resolve things as things evolve, so that is nice. You don't need to do a mesh, that is also an advantage. You have a unified description of discrete and continuous systems, and I think that's an appealing thought, that you can think of these both in terms of continuous and discrete systems, and then you can do open systems, so you can do the exact free space conditions. Sorry for that. I have a study day today. And there we go. But of course, as Lorena was so nice to point out yesterday, we shouldn't oversell. And there's definitely things that makes this less attractive to use. And this is why these methods are not used as a mainstream CFD calculations. And of course, this evaluation of the F and the K's, they pose an n-body problem that scales naively order n square. And then we also learned yesterday that we can do better. We can do order n log n, or we can do even order n. But it's what we found is that to implement these methods is a bit complicated, and it's not so easy to parallelize. And then finally, as these things move around, they may scatter, and if you want to compute gradients on scattered data, that can lead to low convergence. And finally, wall boundary conditions can be tricky to impose. So before we do that, before we go to the continuum, I will show you some results that we did for atomistic simulations. And here's some results going 20 years back when we started doing this, by Thomas Dwerder, et al. And Petros at the CSC lab. So we looked at wetting, so no flow and carbon nanotubes. We looked at imbibition of water in carbon nanotubes and nanochannels. We did Kapitsa resistance, so we did heat transfer as well. There's an example where we looked at the influence of the dissolution of air in the presence of a copper-water interface and looked at how that influenced the Kapitsa resistance. And at the bottom, you see a membrane where we have water on one side, we have a piston, and we push the liquid through to study the validity of continuum approximations. So if we turn to this a little, then here's how that would be produced. If you look at the right, this is the production of this. So you do some doping, you grow some nanotubes with diameters that are pipes made out of carbon. They are 1 or 2 nanometers in diameter. You etch the surface, you put some matrix material, and then you expose that matrix or that membrane to a pressure difference, and you measure the flow rate. And then that flow rate you can relate to the Hagen-Poiseuille flow, and then you can check if you get more or less enhancement compared to the Hagen-Poiseuille. And people did this. Holt in 2006 did that, and he observed that you have an enhancement. The flow flows faster than what Hagen-Poiseuille will predict, and with 3 to 5 orders of magnitude compared to the Hagen-Poiseuille. And the way that we understand that is that the no-slip condition that we usually impose in continuum fluid mechanics is no longer valid if you have an atomically smooth surface, and then you would have that the velocity profile has a finite value at the interface, and you can express that with a slip length, so the extrapolated distance from where the velocity field will go to 0. And you can put that into the Hagen-Poiseuille equations, and then you can write, so you include the slip condition, and then you can convert the enhancement into slip length, and that will give you slip lengths of the order of 100 to 1,000 nanometers. And you can imagine if you do car aerodynamics, if I displace my paint by 100 nanometers, it's not going to influence the drag on my car. But if I have a pipe of the order of 1 nanometer in diameter, then a displacement of the effective surface by 100 or 1,000 nanometers is very significant. So we decided to look at this. We applied molecular dynamic simulations. Here's some details. The main point is that you can see that there's just around 10 atoms across this. So the question was, can we trust the continuum models that we have for this? And there's 3 stages. We have to fill it. We have to fill it on the other side, and then we have a continuous flow. And it turned out that the continuum models really work very well. At this scale, you can compute the pressure that you need to impose on the system to push the liquid in, and that's 120 bar if you believe in Young-Laplace, and that was what we found. You can then, during the filling, you can track what is the position of the meniscus, and then you can fit the slip length from those simulations and this entrance losses that I have over there, this Q times C, and then we find slip lengths of 67 nanometers, and we find a C constant of 1.77, which is in good agreement with theory from Weisberg, and the slip length is a good agreement with what people found before. Then on the other side, you again have a Young-Laplace pressure. You can again use the exact expression, and you'll find, yes, that the simulations match those continuum approximations. And now we can continue, and you can see what is the flow rate as I make the membrane thicker and thicker and thicker. And this is what you observe. On the x-axis, you have the thickness of the membrane, how long is the pipe. And on the y-axis, you have the enhancement. And you'll see for a very short pipes or thin membranes, you have a low enhancement because it's dominated by the entrance and exit losses. So this was the nanoscale. Then you can say, you can also couple that to a continuum model. So we did that. There was an initiative at ETH as well, starting in 2005, where we coupled atomistic simulations to continuum fluid mechanics. Continuum fluid mechanics is illustrated by these blue streamlines, and the atomistic simulation is the red and the cyan dots. This is a challenge because as you couple from the continuum to the atomistic, you need to insert atoms into a dense system. You need to do that without having irregularities in the flow. So this was worked on until 2012, and then we paused that. The other thing you can do is you can learn from what you have done in the atomistic scale and then implement that into a continuum fluid mechanics code, and that's what you see on the bottom right. So this is just a CFD simulation of the membrane that we saw before. And finally, you can go on and you can remain Lagrangian, but you can do large-scale simulations. I'll come back to that in just a few moments. So this is an example of you do just continuum fluid mechanics, but you take into account the properties of the flow at the nanoscale. So you have symmetry bounding conditions, whatever, you have outlet, you have inlet, you impose a mass flow, and then you measure the pressure difference across. And now the nice thing with doing classical fluid mechanics is that you can selectively vary the parameters that you want, and there's not a cross-contamination between different potentials that you would have in atomistic simulations. Here you can vary one parameter after the other. So on the left axis you see the pressure loss as function of slip length on the x-axis. So if you have a low slip length and no slip condition, you have a high pressure loss, and if you have on the right you have a fully slip condition, and it's dominated just by the entrance and the exit losses. And of course, then you can probe into the flow more easily because you have a continuum description. So on the right, you see different pressure profiles as you go through the membrane. And then you can do the very large simulations because you don't have millions of atoms, and you can predict. So the red crosses are the CFD calculations. The dashed line is the fit to the analytical model. The blue lines is our in-house code that we ran first, and the black triangles are another open source code that we ran, and we saw this agreement or disagreement, if you like. And you can look in where's the dissipation. The top picture is dissipation. On the top left, you have no full slip on all the surfaces, so no resistance. The resistance is only at the entrance. And if you go to the far right, you have the no slip condition. And similar at the bottom, you can then study the pressure profiles, and you can try to optimize the losses if you play with the slip length. Then I turned to, as I said, continuum fluid mechanics. What I have done in the past many years ago, the same as Marina and the same as Petros, as I was doing vortex methods, and we did that for bluff body aerodynamics. And they're sort of okay because you have sharp corners on these structures, and there will be separation there. So you don't need a sophisticated model to capture the main physics. So the main physics is I can predict the static lift and drag coefficient, I can expose the bridge section to a motion, I can extract the forces, and I can analyze the forces. And I can also do aerodynamic admittance, so I can expose this bridge to an oncoming turbulent flow, and I can study the influence of that. What I cannot do so well, it turns out, is to do vortex shedding, just a normal vortex shedding with a fixed cross section. And we believe because the flow turns into three-dimensional, and our code is just a two-dimensional code. So in order to do that, we need to go back and revisit what we did. And to do this to handle complex geometries in 3D, the way that we solved doing that was do penalization. So we solve now the velocity on a mesh using FFTs, and you can do free space conditions for that. And then you mark the region where you have your structure. And this is this chi function here that if it's 1, it's inside the structure, and if it's 0, it's outside. And with that, you can then add that as a source term. So you drive the fluid velocity u to the velocity inside the solid v, with a certain forcing constant, which is this lambda, which is if you say a new time scale that you introduce into the flow. If you don't like to solve for velocity, you can solve for vorticity by just taking the curl. And you can see on the bottom, it's just a source term in the vorticity transport equation. So if you do this in 2D, you have to follow the flow, you have to diffuse, and then you have this Poisson equation, equation 19, that you have to solve. And as I said, you can do that very efficiently on a mesh. So you take the particles, you interpolate them to a mesh, and then you solve the Poisson equation, and you solve for the velocity, and then you can interpolate the velocity back onto the particles. And then you get something like this. Here's a illustration, and then you can do different resolution in different regimes, and you can simulate an impulsively started flow past a flat plate, and that was implemented in this particle mesh library that we developed at ETH as well. And you can, of course, quantify. You can say, I would like to compare the drag history as a function of time, and you can convince yourself that you're doing an okay job. Then it turns out, when you read the papers, that people, when they do this thing, they choose a very small time step. And they do that because they realize they introduce a new time scale. And you have to respect the time scales that you introduce. And for that reason, so if you don't do that because you would like to run at the time step that you will normally run at, then you see something like this, that the flow is just going through the structure. And then, so we were concerned about that and thought, what can we do about this to take the large time step that we would like without having a porous meter that really looks very porous? So what we looked at is an illustrated example. You have this vorticity blue and green. You like to satisfy the boundary condition in the green region. What you do with the blue and the red, you solve the Poisson equation, you get the velocity field on the right. You look into the solid and you see there's some velocity there that you would like to cancel. What you can do is you can then locally take the curl of that velocity, and that will give you a source term. And then you can solve the Poisson equation again, and then hopefully the velocity inside will be zero. But it's not fully zero because you don't take into account cross-coupling between the different source terms. So what we proposed to do was iterations, that we keep iterating this process again and again until we have convergence. That will be costly because you have to solve the Poisson equation on a very large domain all the time. But we thought, but the Poisson equation is linear, so we can just split onto a mesh that is only close to the body of interest, and then you only iterate there. So here's an algorithm how you do that, but I hope it's obvious what I'm referring to. So you can do this again, you can compare with or without this iteration, and you see that if you don't iterate, the flow is going through, and if you iterate, it doesn't go through. And you can again compare and quantify and show that things are okay. Again, time history of drag for different tolerances and for different, if you do the conventional stuff. Here's another example. You can stress the flow even more. You can accelerate the flow. So here's a plate that keeps accelerating. And of course there, it's always out of equilibrium. So you see streamlines on the left that are horrible. The red curves are it's really just going through. And on the right, you see a large displacement of the vorticity as you do that. And again, you can quantify. On the left, we have, again, early time drag comparison with a code that is not doing penalization. And on the right, the comparison with Komatagos and Shields for a longer time history. So with that, I hope I have given you an insight in what we have done in simulations across scales, from the nano scale to the continuum scale. From the nano, we can often just assume continuum fluid mechanics, but then change things at interfaces, in particular at solid interfaces. And then hopefully also inspired someone to view flows Lagrangianly and maybe go with the flow and not get stuck on a mesh. And with that, I would like to thank the collaborators, both at ETH and in industry and other universities, and my DTU students. Thank you so much.
Thank you very much, Jens, for this great talk. Now, just for the orientation of the audience, we're going to start with some questions that Jens is going to answer, and then at the end of this session, you will have a chance to ask him questions about the presentations that you've heard or anything that we've discussed here. So, to break the ice, some quick multiple choices from two things: GPUs or CPUs?
CPUs, because I chose, when I went back to Denmark, to look at not speed, but look at order. And so I was trying to promote to go to higher order than just to go faster. And for high order, you don't need fast computations.
How about Lagrangian or Euclidean approach?
That's a hard one. So I like Lagrangian ones, but when I really do, so I do a lot of different things, a lot of applied research. And if someone comes and says, can you do a container ship? I would not use a Lagrangian method. So a lot of the stuff we do now is with Eulerian methods.
And how about your own code or some open source or commercial code?
That's also a good question. So we do both. We both had different codes in the Lagrangian description. We have OpenFOAM, which is open source, which is great. And then we have commercial codes. And there's pros and cons to all of them. So I would say I use all three.
And how about your first HPC moment, so your first experience with flow computations and in particular high-performance computing related to that?
Yeah, so I think the first moment of computational fluid dynamics was when I was doing my undergraduate studies. And I think in the 7th semester, something like that, we were doing a finite difference approximation or simulations of a granular bed. So like a two-phase calculation doing finite differences. But back then, the graphics was virtually non-existing. I mean, you had either a green screen or an orange screen, and you couldn't see anything there. So it was not that inspiring. And when we had to visualize, we had to make a printer, pick up a pen, and draw the particles. So I think it was only later at my master's degree when I was doing a mesh generation and then a structured finite volumes that the graphics was so mature that you could actually see that the flow was on your screen. In terms of HPC, I think the first real experience was with the CSCS, the SX3 and the SX4, the NEC machines, where you could feel that you need to hold on. Once the code had vectorized, you really needed to hold on because it was fast.
That's great, and it was great to see the visualization that you've shown us here of your current research. It's also great to hear for the junior members of the audience here at the early stage of their career about your beginnings. And can you tell us why is this an interesting research field for you? What motivates you to keep doing it?
I thought it was obvious, but it's true. I mean, so we have this nonlinear term that we don't like, but then yet we love it because it produces all these beautiful pictures. And then I'm in fluid mechanics. I'm not in pump manufacturing or in wind energy. I'm just in fluid mechanics, so I am allowed to do all kinds of flows. So I'm doing flows with the Danish Olympic team, doing kayaks and sailboats. I'm doing super tankers or flows in biology with small little critters that are swimming. So I think it's the richness of what fluids has to offer that is inspiring.
And the richness of applications, as I hear.
Oh yeah, there's plenty. Yes.
That's really inspiring. And a little bit more about your personal and professional career. So when did you decide to follow this research direction? You mentioned already your first experiences with HPC, but did you know it right from the start of your research career, or was it something that developed a little more along your research career, this direction that you were talking to us about?
Yeah, I think all of us have this, that we meet people and then we take a turn, and then we meet someone else, and we take another turn, and in the end we end up here. And so I remember when I did my undergraduate studies, I had signed up for solid mechanics. And then my father told me, won't you like to do energy instead? I thought, maybe he's right. So I took and I changed the cross to energy, and that was where fluid mechanics was. So that was the first turn. I think the most important turn was coming to ETH. Because, I mean, if you don't go into academia, you're not going to do academia. So coming here was a breaking point to meet all these great people and to have the resources there. That was what defined it.
That's really great to hear. And now let's circle back to the challenges in your research. So you've shown us several applications. What is the big research question you would like to answer over the course of next 10 years or more?
Yeah, that's... So what should I say? So I'm not doing a pump, and I'm not doing a wind turbine. So if I can make the best pump, I'll be happy. I just like to solve problems. And so, but what I would like to do is I have a long time collaboration with my former PhD supervisor, who's still very active, and he was interested in doing simulations of flows at small scales with biology. And I think that's a very inspiring area, also because it doesn't have all the models that we have if we do diesel combustion. I mean, diesel combustion is a zoo of models, and all have their approximations. When you do biology, what you need to know is how does the critter, as we call them, look like, and once you know how they move, you can do simulations. So I'd like to dive into the biology more than what I've done so far.
And what would be some applications?
That's what we are discussing right now. It could be to do artificial filters. So if these ones would pump, I think 1 million times their volume a day to filter the water. If we can do something that can pump 1 million times its own volume per day efficiently, then I think there's room for good filters. So that's just one.
And what's the scale of these simulations that you did? What's the scale of these simulations? Is it comparable to what you were telling?
So yeah, it's not atomistic, it's simply continuum fluid mechanics. But it's complicated by the fact that you have large displacement. So you have flatulets that are moving, you have filters around it. So it's more the morphology of the critter that is the challenge. And then you move in a very low Reynolds number flow. So it's interesting to see that you have this little critter in the simulation and it's speeding its flatula, if the moment you stop the flatula, the flow stops. So there's no inertia. Sorry. So that's a challenge.
Is there any chaotic behavior that you would be worried about now that you were mentioning?
Are we sorry?
Is there any chaotic behavior that you would be worried about there? Or?
No, not I'm aware of. The other thing we'd like to look at there is, so what we're doing now, we're looking at how, we had a paper coming out 2 weeks ago, and we were looking at how these feed, so how do they create a current that would make them catch prey, and how they swim, and what noise they produce. And we were trying to see traits of those. And the way that we treated noise is, there was some approximations associated with that, and it would be nice to look into if the way that we perceive noise at that scale is accurate.
That's really interesting. Thank you for sharing that. Now, we've mentioned in the quick introduction Lagrangian methods versus Eulerian methods. So how about, what are the pros and cons of Lagrangian methods? You mentioned a few, but maybe if you can briefly summarize for the audience.
Sure, yes. Yeah, so you can say, so there's two types of Lagrangian methods. One is you solve for velocity pressure, and that's very popular these days because you can in principle get the free surface for free, some people claim. So you can have a large, you can do the free surface for free. But of course, there's never a free lunch, and when the particles get far apart, convergence goes out of the door. And so that's one, you can get things efficiently without creating meshes. For the vortex methods, what we like there is if you have flow past an airfoil, you have velocity everywhere and it varies everywhere, but the boundary layer is localized, hopefully close to the airfoil. And it only has vorticity very close to the airfoil. So if you write a formulation where you only look at the vorticity, then you don't need a large mesh going away. Sorry, but so in that sense, it's efficient.
All right. And now I also want to hear more about the challenges to multiscale coupling of atomistic to continuum scales. And if I understand correctly, you abandoned it. And what's the reason for that?
I think we took a long pause, at least, because we did a lot of good work. There was a very talented PhD student. He started 20 years ago, and he looked at that. And so you have to realize you have a dense system, and if you have a flow going through, you have to insert atoms into that dense system at the right temperature and then not disturb the flow. And it turned out, for the cases that we had chosen, that the main computational effort was still going to the atomistic simulation. So what we would do if we would resume that, I guess, is to be able to do more complicated couplings and not just a little box or a sphere, and then look for applications where you have a strong coupling on a large scale where the CFD or the computational fluid dynamics would help you, to a small scale where the atomistic would be important. And we didn't really go that far as to explore that part. So it's paused, let's say that. But there's a lot of challenges to take it further, I would say.
Nice. And now we mentioned your own code versus commercial or open source software. Can you elaborate a bit more on pros and cons of developing your own code or using something that is already on the market and contributing to that?
Yeah, so what I appreciate so in the old days, and I'm getting old, everyone would have their own code, because then there was no open source or no commercial codes really available, so you would write your own code. And if you do that, you spend a lot of time doing that and have fun with that, but you also know exactly all the tricks of the trade. You know exactly what's going on. So that I appreciate when people write their own code. Then, of course, at some point you get tired of implementing all the models that people have already implemented elsewhere, because you need to catch up. So you need to do heat transfer, you need to do turbulence, you need to do radiation. All these things is not really research, it's just re-implementing existing models. And then at some point, if you have to do that, you say, okay, let me maybe just pick an open source code or a commercial one. And the drawback for the open source is, of course, there's not a big manual, but there's a nice forum that you can connect to. And for the commercial codes that we're using, the manual is 12,000 pages. So you don't just read it from the beginning to the end every time there's a new release. So the drawback there is you cannot see the source code. And you have to trust and you have to read the manual carefully to understand what's going on. And it's my feeling now, maybe I'm biased from my group, is that when people say, I need to have a spray, so they go in the manual and they say, I need the spray, and there's a button called spray, and you click on the spray, and then you need a breakup model, and there's two, and you pick one that was based on literature surveys. But the underlying fundamental understanding of what is really going on is sometimes lacking. So there's a schisma there between having all the software already implemented and really understanding the details. And sometimes they are important. Well, I would say they're always important. The details are always important, so you understand exactly what's going on. Otherwise, you're just turning knobs and then looking at the result.
And what would you say on the point of view of efficiency of code?
That's a good question too. I know that I have good colleagues in the wind department at DTU, and they have their own in-house code, and that's very efficient because it's written for exactly that purpose. But if you need something general where you can handle very complicated geometries and you don't want to spend a month doing the mesh, then the commercial codes are really efficient nowadays. So for instance, just before coming here, I had a class I was teaching 60 students for 3 weeks non-stop to how to use a commercial code and also to tell them what is going on behind the scene. And the first 3 weeks, we were giving them lid-driven cavity, turbulent flow in a pipe bend, and then a transonic aircraft simulation. And I thought they liked that. And then the third week, I told them they can do whatever they want to do. So so some people would do frisbees, flying in space. Some would do bridge aerodynamics. Some would do mixing. And of course, this you cannot do if you write your code yourself.
It's really encouraging to hear that even though full-time, but in 3 weeks, then one can become professional in that type of simulation code. Now, we were talking about these details of your simulations, but I want to zoom out again and go back to the big picture. So you were mentioning Lord Kelvin and 19th century work on which you are basing your research afterwards, and the whole field has developed from it. So what is the research you want to be remembered for when people in 100 years talk about this research area?
Maybe if I can say 2 things.
Sure.
Thanks. So the first thing is that I hope they would appreciate the at least sustained effort we had in modeling simulations at this scale. And the reason why I say this is because I want to say that resources are important. And if you have good resources, like you have here, with infrastructure and people, then you can do good research. So you can do the extra mile, you can run the extra simulation, you can make sure that everything is okay. You also have time to write your own code. We did that back then. And if you do that, as I said, then you get to know all the details. And finally, the reason why I think hopefully it will stand the test of time is that we never really heard anything. I mean, in the lab that I was in, we never heard things. We were efficient, but we didn't hear anything, so we really checked that everything was okay. So I hope that would prevail, and people will see at least. I don't know how important the contribution is, but it's at least it will stand the test of time. And the other one I wanted to say is that I'm not an applied mathematician. I'm an engineer, and maybe I'm a CFD specialist, if anything, or applied CFD specialist. But we had one paper in an applied math journal that I liked, so I thought that could be something to hope that would stand again test of time. And it had to do with that we were trying to move forward from low-order methods to high-order methods. And you can do, if you do spectral methods, you have super high accuracy in periodic domains. And what we wanted to do was to go to open space. And you can do open space. There's a beautiful book of Hodney and Eastwood where they show how to do that. But you have to sample the Green's function in real space, and then you have to take the Fourier transform. The problem is, of course, these Green functions are often singular. And then the question is, what do you do at the singularity? And Hodney and Eastwood said, just put a number there. And you do that and you get second order, so it converges. But we were trying to go further because our interpolation was third order. So we were suffering that we were losing an order when we went to the FFTs. And then we were struggling, and then I remember sitting in the office, and I realized that when you don't do FFTs, if you just do n square, naive, then people did that 40 years ago of how to do that. You take the singular function, you modify it with a kernel of a certain order, and then you get higher order methods. So when I realized that, I put this into Maple, and I gave the result to my PhD student, and then he came back the next day and said, now we have 8th order. So this very simple solution, because normally in CFD, you'd have to do verification, you change the mesh, you change the time step, you change your turbulence model, you make sure everything is correct, but it's tedious. And here it was just an idea, and then a simple implementation, and then you show that it works. And I hope also, because it's just solving the Poisson equation, that there's other people who have a Poisson equation that would like to solve it with high order in open space.
That's really an interesting fundamental development, which you probably use in your many applications. Yeah. I heard the word Maple. Did Maple withstand the test of time? Are you still using it? Or
I don't know. I thought I would try maple. I haven't really used it much, but
Okay.
it served the purpose.
All right. And let's stay in this big picture domain. So what do you think will be the breakthrough that makes the general public aware of the importance or relevance of high-performance computing in the field of computational fluid dynamics?
I think if we can solve a big problem that people will realize. So now with the energy crisis, maybe people will realize that there's wind turbines are driven by wind, and wave energy may be a future, or solar. So I think if we can show the public that research matters for this very critical problem that we face right now, then I think they realize that you cannot do that on your phone, but you need a big computer, then I think there will be an appreciation of that. That's my hope. So you can also say this climate challenge is a huge challenge and it's not very pleasant, but for research it's an opportunity to do something that is disruptive. That you don't just increment your application by 5%, but you have to do something completely different. And that's at least inspiring.
And if I hear correctly, you're saying that the new high-performance computing resources are needed for that in order to...
Yes, I remember once I was interviewed by people who were, maybe I shouldn't say that, but now I'll do it anyways. I was interviewed by people that were responsible for infrastructure somewhere. And then they asked me, would you ever have a computer that is so fast that you don't need a faster computer? And I said, I don't think that we will ever reach that point. So we can always use a faster computer, I would say. And you can solve bigger problems better. So I think that's really a key to success in science, I think.
Excellent. Anything else you would like to add?
No, I can take questions if there's any questions, but thank you very much.
Thank you very much for your excellent presentation and for this discussion.
Thank you.
And at this point, I would like to take some questions from the audience. So are there any questions related to our discussion or to the talk that Jens previously gave in presenting his research?
Hi, I'm
Yes,
Johnny
please.
from the
Jonathan
Harvey
first.
Center. It's okay?
You already stood up. All right, you're going to go next.
Right, the question is very simple. What do you think about AI for science?
What, sorry?
AI for science.
So I think it's very exciting. I think that something good will come out. I was in a great group doing GPUs and artificial intelligence or neural networks. So I thought I don't need to do that as well. So far I have stayed away from it, but I can definitely see that there's a great potential for that. And as in all elements in science, there's always a hype. And you can frown on the hype, but I think the hype moves people. And it moves people into an area that they were not in before, and that could maybe do some cross-fertilization of the different disciplines. So I think overall it's fine. And we just have to realize that there's a hype, and money will be spent in different ways, but something I think will come out of it.
Thank you.
You're welcome.
I saw another question here. Yes, please. Thomas?
So, thank you for the nice talk and overview and also the questions. I would like to enter now into this kind of simplistic discussion on computer architecture. CPUs versus GPUs. So my first question is, you chose CPUs, you gave a reason. Do you mean vector CPUs? Because you also mentioned the NEC, or the good old days. Should we go back to those good old days?
So I think, since I stayed out of GPUs so far, although I think it would be fun to try to program it myself, then I was happy to see that the Fugaku computer came out, which I believe doesn't have graphics card, but just a very, almost like the old days processor. So maybe, for me, I thought maybe my pause on the GPUs could pay off, and I didn't have to spend the time doing that. Yeah. But I think it would be fun to do this, and I'm not sure what the future will bring.
So the material cost of Fugaku is similar to the Coral systems, like 500-600 million. Mm-hmm. And then the fact that you have a processor that does not have a big other market, you have to add another 500-600 million. So you're talking about 1.5 billion.
Yes.
Investment.
That's true.
And just be mindful
yes,
of that, okay?
Yes, yeah.
And so somehow we have to figure out where we get this money. If we go that scale, in Switzerland, we're kind of an order of magnitude smaller.
Yeah, yes.
And I know Europe is trying to reach high, and we're going to see what comes out of that.
Yeah.
You gave this kind of surprising answer that you like high order methods, and I completely appreciate that. That makes a lot of sense. Now, high order methods typically localize your computation. You have to move less data, and you have more local computation. And so then I don't understand why GPUs would not be good for that.
They will. No, they will. There's no problem with GPUs. It was just my research focus was first doing a high order method, and then eventually apply that to something that required GPUs. So it was just a matter of priority.
Okay.
No, it would definitely, because it's just an FFT.
Okay.
So yeah, if you can do FFTs on the GPU, and you can, then it will be fantastic.
Okay, good. So thank you for the clarification then. And regarding the software discussion, we have a struggle that's probably, well, older than I am, and I'm probably a bit older than you are. We have this struggle of whether closed source works for anything or not. And the experience, particularly in science, I think, is more on the side of open source software. So how are we moving the fluid dynamics and the computational mechanics, computational engineering community to join the open source movement?
We are. I mean, there is a long history of OpenFOAM, which is an open source CFD code that is used by industry and by universities. And we use that as well for some simulations where we don't have to create complicated meshes. So it's there, and it's been there for a long time.
And Fluent?
Fluent is not open source.
Okay. So that's exactly my question. How, we are like the NVIDIA colleagues. What is the code that's giving us a headache? ANSYS or?
It could be.
Okay.
Yeah.
So that is I'm sorry, maybe there are some people from the company who is developing this that are here that can talk to me, but this is a code or a software package that's giving a headache to almost anybody who wants to innovate on computer architecture.
Yeah, that's probably, that could be.
And that's not good, because we are facing physical challenges that are being answered to by very smart computer architects with architecture, and then we have software in engineering that is just keeps us in the Stone Age. So how is engineering helping us to get out of the Stone Age into modern software, modern architectures?
Yeah, so I'm not using that software. I'm using another software that came out of London that has a long tradition for doing fluid mechanics, also for teaching. Okay. And they developed a code that was written in 1477 back then. And then at some point they realized that that was probably the end of that lifetime, and they rewrote everything. So now it's written in C++ and in Java, and it runs on thousands of cores with I would say, good efficiency. So we had a praise grant 2 years ago, I think, where we were doing diesel combustion and alternative fuels. And we were using both OpenFOAM and this software from Siemens, which is called Dissipation Plus. And both were performing very well on this machine. We were running on 1,000 or 1,500 cores non-stop. So we were burning, I think, 20 million core hours in a year. So that was very efficient. I don't have personal experience with the other software, so I cannot comment on the efficiency of that.
I think this is an important comment here, that we need to move to open source and modern software engineering. Software engineering, I can say, has advanced a lot in the last 30 years or so since I've been in the business. And on computational science side, we've been slow in adopting these methods, but it's very good that you support this. And
yeah, I do. And the software, the commercial software that we use is also now CUDA aware, so it can speed up the calculations. I've done some preliminary tests, and it looks pretty good. It's a factor of 10 in speed up, at least on a single node.
Okay.
Thanks very much for this comment, Thomas. I saw a few more questions here. Did you, Jonathan, want to ask?
What has just been said, there's another alternative to OpenFOAM, which is called Code Saturn. There's much less physics in it, but he already ran on 3 million threads in Argonne, so he's massively parallel for CPUs. Yeah. And now there's a push to put it on GPUs. So a few years back, with the help of Samuel Antao, who used to be at IBM, we could run on 512 nodes on Summit, so 3,000 GPUs. So that could be an alternative if you want to go big.
Yeah, exactly, yeah, there's sometimes domain-specific, or at least codes that grew up out of domain-specific applications, and then generalize. So you should always look at the tool at hand. I mean, I had a PhD student who was going to do oil and gas excavation back when that was still an issue, and he looked into what software would provide the models that he needed. And he ended up using ANSYS for that reason. It had the physics that it needed, and the other packages did not. So you have to choose the tool carefully such that you use the best of that it has the physical models that you need, and of course that it runs efficiently on the hardware that you choose. I agree.
Thank you.
Thank you.
Jonathan?
Can you, two questions.
Yeah.
You were talking about, Lagrangian methods or Eulerian methods.
Yes.
Have you looked at hybrid methods, moving mesh, those kind of things, Honore tessellation?
Yes, you can say that we already do that in two ways. If we do the pure Lagrangian methods, we still have a mesh, because if we don't have a mesh, then the particles get too far apart, and then we lose convergence. So if you saw one of the animations, you will see that you have these particles, they move, and then they still look regular after a little while. And that's because we do remeshing to ensure that we have convergence. So we have a hybrid there. Also for the other application, I mean, if you do a diesel engine, the mesh has to move because you're opening and closing valves. You are moving the mesh, so we definitely do that as well. And you either then use AMR for refining the mesh where you need it, or you do remeshing when you find that the mesh is too distorted. Right. So all this is being done, and that is required to do these calculations.
Okay, thanks. Yeah. And so the other question was about maybe earlier work where you were doing MD simulations on the microscale, and it looked like you had these, it was basically water you were simulating, right?
Yes.
I mean, so what kind of water model were you using? And in the years since, I guess, you started, there have been much more complicated water models developed, and how does that, or do you know how the choice of water model, how that affects your larger scale simulations as well? Yeah,
that's a good question. I mean, we haven't gone back to check the early results by running them again with a different model. Now so back then we were using SPCE because it seemed to have the properties that we needed in terms of viscosity and self-diffusion, as I remember. But now we use the TIP4P 2005 because it has better properties in terms of thermal capacity and heat transfer. So we are up to date with the water model, but we are not going back and really reconfirming that the older studies could have suffered from that.
Yeah. Okay. Thanks.
Thank you.
Yeah. My question is that the astrophysics and cosmology community, in that community, the fluid dynamics is also relevant, specifically also turbulence, and they've developed several codes, often with a focus to deal at enormous scales. Yeah. And so have you looked at these codes, and if so, could they be useful for engineering applications as well?
At least we were definitely inspired by astrophysics and how they did the long-range interactions. That's true. They are also doing SPH, and there but they didn't remesh the SPH because I guess it was not important in that field. In our field, if we use SPH, we need to do something to ensure that the method converges. And then, of course, So what I looked into back then was if you in astrophysics use periodic boundary conditions or open space. And my impression when I looked into it some 5 years ago, that it's mostly periodic systems. And it could be interesting to explore that further to see if our higher order Poisson with open boundaries could be useful in the astrophysics community.
Thanks.
Thank you.
I just want to make a comment what Thomas said about open source versus closed source software, and I think the reason the reason why people are still using the codes that are not efficient is that the commercial companies behind it are treating the software as a key that fits to every lock, to every problem, and maybe there is a lack of collaboration between teams that have the community that has own software that is really targeted to specific problem, and how do you comment on, is there collaboration between industry and let's say research community? Is industry approaching you, or are you approaching the industry to show the new capabilities, or how does it work?
So we have a very close collaboration with industry. I'd say 90% of our master students are with industry. So, and they do CFD, so there's a very close collaboration. There's also a collaboration between the CFD providers and both the industry and universities. So one example is that we're doing some wave energy converters, and we need to run wave simulations for a long time, and we have a device in there, we want to extract energy. And it turns out that if you do a simple RANS calculation, Reynolds average Navier-Stokes, which is known not to be super accurate, you have a divergence of viscosity in your domain as you run in time. And my colleagues found that out 5 years ago, and they published a few papers on that. And when they did that, I sent that to the support at Siemens. And then I realized, so now again, it's coming back to us. We have this problem. And if we run for a very long time, then we see divergence. And now they're implementing that. So I think there is a communication between them.
We will have time for another question too, but let me just check whether there are any questions online. Eleni?
See if I can. Yeah, so not yet, but I could exploit this to ask my own questions.
Please.
So I was wondering, you showed this work on very on multi-resolution, multi-scale forward simulations. And of course, you work with industry, you're driven from actual problems. So I'm wondering, what is the role of data in conjunction with these simulations? Is it mostly validation? Are there other ways in which you exploit data? And if so, how do you extract, or is it possible to extract data at all of those scales that are involved in your simulation?
Yeah, so I would say from the very small scale, we don't do experiments, and I'm not in contact with people directly who do experiments. So there we rely on literature to compare, like with the slip length and enhancement. For the large scale of industry collaboration, there's always a dilemma between, if you work with industry, they have NDAs that you need to, and publishing can sometimes be difficult, and so that's a challenge. But it's nice to do, so it's important to do validation. Right now I had 2 master students, and they contacted a shipyard and got access to the ship, and they scanned the whole ship and the propeller, and then they scanned also the roughness on the ship and the welding seams. And then they simulated the ship with the propeller turning and the roughness and the welding seam, and they submitted their thesis as a paper. And it was well received, but of course, it's confidential. The ship, we cannot share the CAD drawings of the ship or of the propeller. And that's a dilemma it would be nice if industry would realize that we are here for them and not to steal from them.
Since you make this point, actually, it's not just data that is hard to share when they come from the industry, it's also even the models. The wind energy and the wind turbine industry is a very good example of that. And you're, being in DTU, probably these are discussions that you may have.
Yes.
But I guess we would need open science to span through those modalities.
Yeah. But I mean, it's clear if you're an industry and you have a strong competitor, you want to make sure that what you're working on right now remains confidential. So there's a dilemma there. But I think it's rewarding to work with industry because you know that you're working on problems that would be relevant tomorrow and not in 20 or 100 years as well.
Fully agreed.
Thanks very much for this comment, Eleni. I think it relates very well to the last point that Jens made of making an impact related to climate research as well, or effects of the climate. One last question, if there is any. Yes, please.
So with respect to the discussion on Lagrangian versus Eulerian, I work in the field of atmospheric dynamics, and fully Lagrangian methods are just never used. So with the techniques you were discussing, for example, remeshing techniques, are we at a point now where we could actually solve the equations of motion of the atmosphere, on a very large scale, obviously, with fully Lagrangian methods?
I guess so. I was once, so when I did my PhD, after that I went to the Danish Meteorological Institute, so I worked for 1.5 years in the Met Office. And I did realize that they were doing what they call semi-Lagrangian methods. So they were doing advection schemes that sort of resemble what we do. You can say what we do is maybe resembling similar Lagrangian methods. So in principle you can, but as we add more and more physics, and in your field I guess you have complicated physics, then to add that to the equations, I'm not sure what the gain is compared to a semi-Lagrange advection scheme.
Okay, so semi-Lagrangian is very, very frequently used in the field. I'm talking about fully Lagrangian particle methods.
Yes.
And so I guess your answer is probably we're not there yet.
I think that's correct.
Okay, thanks.
Thank you.
I want to thank Jens for all his answers, and thanks to the audience for the questions. We will now move on. Eleni.
Yes, I want to invite everyone to congratulate both Jens and Marina for this very nice session.